To build 211 meters into the Persian Gulf, engineers first had to construct the very ground they were building on. This $600 million Leeming megastructure sits on a site that, just a few years ago, was under the surface of the sea. The site is located on an artificial peninsula in Qatar. To create this landmass, dredgers vacuumed the marine seabed and stacked sand into dry land. The severe geometry of the building was dictated by a local architectural mandate. The curved profile of the two towers is modeled directly after the crossed swords found on a Qatari coin. This animated cross-section shows the reclaimed site's stratigraphy. The top 20 meters of loose sand and marine clay have virtually zero bearing capacity. Apply a skyscraper's weight, and this soil instantly shears, taking the structure down with it. To stabilize a 36-story tower, the engineering teams had to design a foundation that bypasses the top layer of earth. The solution was to drill 2,670 individual board piles straight through the unstable marine clay, anchoring them 35 meters deep into the solid rock below. When cutting a shaft through saturated clay, hydrostatic pressure from groundwater pushes against the empty space, threatening a cave-in. To counter this, engineers flooded the active boreholes with bentonite slurry. This dense fluid exerts equal outward pressure, stabilizing the walls. With the shaft stabilized, a 35-meter steel rebar cage is lowered with mere centimeters of clearance. A tremie pipe then descends to the base. Concrete is pumped from the bottom upward, displacing the lighter slurry until the shaft is full. Any air pocket or segregation trapped at that depth results in total structural failure of the pile. To guarantee the load path, every single shaft was subjected to sonic integrity testing. Combined, these shafts create 50,000 linear meters of subterranean steel and concrete, forming the anchor point supporting the physical reality of the tower above. With the pile set, crews excavated a 48,000 square meter pit to a depth of 10 meters to form the basements and mechanical plant rooms. Digging this deep next to the Persian Gulf exposes the site to massive lateral and upward water pressure. The ocean actively tries to reclaim the void. To hold back the sea, the perimeter was secured with interlocking secant piles, reinforced by a 1.5-meter-thick diaphragm wall that operates as a massive watertight dam. If a crack allowed Gulf water to breach the excavation face under pressure, engineers injected expanding grout foam directly into the leak, sealing off the flow instantly. This cross-section shows the groundwater's secondary threat. It constantly pushes upward against the floor of the basement void. Engineers countered this buoyancy by casting a 400-millimeter concrete slab, bound by two dense mats of steel rebar, permanently pinning down the groundwater. The basement acts as a rigid, pressurized vessel, engineered specifically to withstand the continuous hydraulic lift of the Persian Gulf. Above the basement sits the ground floor transfer podium. This massive platform gathers the asymmetrical gravity loads from the leaning towers above and distributes them evenly to the pile caps below. To span the 22-meter-wide ballroom void on the ground floor, these transfer beams reach depths of 4.8 meters and are packed with tightly bundled 40-millimeter rebar. This model highlights a thermal problem. Dense C60 concrete generates immense heat as it cures. If the core exceeds 71 degrees Celsius, rapid expansion will tear the beam apart internally. To fix this, engineers pumped chilled water through surface pipes, forcibly dropping the core temperature. Managing the immense physical weight of the concrete was dependent on strictly controlling its chemical thermodynamics first. The main superstructure relies on 8 heavily reinforced concrete core walls. These act as the structural spine, carrying the cumulative weight of the floors and the facade. However, to achieve the required sword shape, these cores are not vertical. They lean aggressively outward, increasing the angle of deflection with every floor poured. This extreme curvature creates a severe structural risk for the climbing formwork, the temporary molds holding the wet concrete in place. As shown in this fluid dynamics diagram, wet concrete acts as a heavy liquid. When the mold leans outward, hydrostatic pressure concentrates at the overhang space. Filling at standard speeds would violently rupture the formwork, blowing wet concrete out over the site. The only viable solution was to deliberately restrict the pour rate to a crawl of just half a meter per hour. This delay allowed the concrete at the base to stiffen enough to hold the weight of the fluid pouring in above it. The demands of the architectural geometry forced the construction teams to rewrite standard scheduling to accommodate the fluid mechanics of the materials. Moving outward from the cores, the leaning profile dictates that each of the 36 floor plates follows a specific, non-repeating geometry. Standardized repeating molds were useless. The contractor had to manufacture 10,000 square meters of custom table forms to cast the slabs. The structural steel connecting the leaning exterior columns to the central cores required each beam to be CNC machined with a specific curve radius derived directly from the digital model. This isometric diagram demonstrates how asymmetric loads are supported. Small cylindrical shear studs are welded along the curved steel beam's top flange. When the floor slab is poured, wet concrete encases the studs, creating a mechanical interlock once cured. This composite action binds the compressive strength of the concrete directly to the tensile strength of the steel, effectively doubling the bending resistance of the floor system. Extreme asymmetrical loads demand highly precise, multi-material integration across every horizontal span. Reaching a peak of 246 meters above the original bedrock, the final major task was sealing the building's exterior envelope. Due to the continuous curve of the tower, none of the 5,000 unitized curtain wall facade panels are identical in size. Each uniquely curved CNC-bent aluminum frame was GPS tagged at the factory and hoisted into a mathematically preordained position on the slab edge. The mounting brackets cast into the concrete are engineered to absorb physical movement, accommodating thermal expansion from the intense desert heat and lateral seismic drift. The facade functions as a flexible mechanical system designed to breathe and shift with the environment while maintaining the building's thermal seal. The success of this structure relies on an uninterrupted gravity load path spanning from the sky down to the earth. This wireframe traces the entire load path. Facade weight travels horizontally through slabs to the central core. The immense load transfers downward along the curved spine. Hitting the podium transfer beams, force spreads across massive pile caps, channeling through board piles into solid bedrock. This megastructure stands because its engineers methodically identified, isolated, and neutralized every extreme boundary condition, from boiling concrete and ocean hydrostatics to severe asymmetrical gravity, long before the first floor was ever poured.